Is it on?
It's on. Yep.
Great. All right. Next, we have Elias, who will be telling us about magnetic fields and MHD around black holes. So.
All right. Thank you so much, Zach, and thank you to the organizers for having me here. Very excited. So what I was tasked with presenting today was to talk a little bit about, how do jets work, how does MHD work, how does it apply to some of the very nice tools that are being presented here. And so what I thought I'd do, rather than giving like a very formal type lecture, I will basically go in and I will show you in different toy examples kind of the more exotic sides of MHD. And maybe by going through them, ultimately, if we have time at the end, we can understand sort of, what this picture actually means and what the different elements tell you and how magnetic fields can alter, let's say, the evolution of two black holes in a binary. And so kind of start out with, if you don't think about MHD a lot, there's a lot of good motivation to do this in the context of high energy astrophysics, numerical relativity, and related fields. I just listed kind of an incomplete list here based on what I find exciting, but there's more things you can do. For example, one thing that we'll talk about today, because talk a bit about jets is, for example, how do you understand, let's say, here on the top left, this is the Geminga. That's like a moving neutron star, and you can kind of see it has a jet. It has some disk around. This is a composition of X-ray and infrared. The X-ray was done with Chandra, and you can see that kind of there seems to be something bending the jets. That's something we will actually understand in kind of a toy calculation that we've done, which you can see over there. I'm going to talk very briefly on how that applies to neutron star mergers, in particular, how you can understand winds and jets launched from stellar remnants within kind of the same framework and language that you use for jet launching from black holes. There's also some excitement recently, again, about magnetized shocks. I'm going to talk a bit about those. Those are, I think, interesting if you think in terms of the galactic magnetar or in terms of certain GRB models. And then I'm also going to talk a bit extensively about potential non-thermal emission channels. For example, if you zoom in on the black hole down there on the right, you can see there's something weird going on, something connecting to it. And we're going to understand some basic processes of reconnection. Interestingly, I think most of these things that I'm showing there, you can actually simulate using the tools that you all developed. So I hope I can spur some excitement for doing that. OK, so I will not talk a lot about kind of the numerical or technical details, but what would be great is if you can just interrupt me at any point and just ask, like, how did you do that? Or, what specifically enters into that? Basically, most of the physics that I will describe here is just described by those equations, which are the ideal MHD equations. If there's time at the end, I can tell you sort of what the assumptions on those are and maybe how you could modify them to do different physics. But by and large, all of the basic principles of how you launch relativistic outflows entirely come from those equations, which is conservation of stress energy. That gets augmented with the magnetic field over here. This weirdly looking equation down there with B and U, that's just written, basically the induction equation written in co-moving variables, and then you have conservation of total stress energy. And so, principle, you can just download any of the codes, would come with Einstein Toolkit, set some initial conditions, hit play, and then ask what would happen. But what I want to highlight first is when you switch from hydrodynamics to magnetohydrodynamics, there's one thing that can fundamentally change. And this is the importance of how strong, weak, or kind of moderate the magnetic field is relative to your fluid flow. This kind of what we'll discuss today in a set of examples. And if you kind of want to see this in a kind of ordered way, one thing you can do is you can think about the system now, because you have a magnetic field as having an order parameter. Right? And just as in terms of, if you think it as a phase transition as an order parameter, and the natural one, as we'll see, for example, if you want to think about jets, will be this one over here. So B squared, that's like magnetic energy density, and then you compare that to rho. I should have added C squared, but we all like C equal to 1, so maybe that's OK. And that will basically tell you how important is the magnetic field relative to the fluid that you're putting. And you can see that I'm spanning a range of values here going from 10 to the minus 3. This means fluid is very important. Magnetic fields maybe not so much. It's only like less than a % level contribution to a regime where the magnetic field is up to 1,000 or more times stronger than the fluid. And those regimes are some that don't quite behave very intuitively. And we'll talk a bit about those too. And if you want to take some of the examples that we've seen before, some that you might also be interested in studying on this line, then, in the in-spiral, magnetic fields maybe don't matter so much, at least for the orbital dynamics. They may matter in terms of other emission you could get from magnetospheric transients, but let's ignore that for a moment. If you go into the merger, you'll amplify the magnetic fields, and depends a little bit in terms of what you assume which processes operate. But by and large, most of this picture here for the remnant and the accretion disk, you kind of move to about 10 to the minus 1 or so. And then when you would want to launch an outflow, you kind of have to go, as we'll see, at least to something that's larger than 1. But we'll go to the details of how that works. And then as you go to the very, very far end, you get into a regime where even your equations might break down. If you think that, here the magnetic field is just a small correction, there it's very large. And this regime, interesting things can happen, and we're going to see them. And in particular, if you're interested in sort of what happens, say, around an actual neutron star that emits radio signals as a pulsar, I can already tell you may not want to use the equations that we're talking about, right? So then here on the right of this plot, you have to go at some point to kinetic theory. Okay, and then at the end, if we have time, I'll tell you a bit about what you can also do with black hole binaries in that context. And now, if you wondered why does this talk have a weird subtitle, and I talked about rubber bands and ropes or strings and crowbars, that's because that's literally what you can imagine the magnetic field lines to do within this plot. So if you're here, the magnetic fields are like a rubber band. The fluid, or basically you with your hand, can just like stretch them around. They have some tension, and that's important if you want to understand feedback on the flow and angular momentum transport. As you sort of move to this intermediate region, the field lines become thicker and thicker, so they harden. You can still kind of wrap the rope around, but it already is quite sturdy. And then at the very end, what kind of this weird regime is, the magnetic field line is really more like a crowbar or a very hard rod. There's not so much you can do with it, but if you do something to bend the crowbar, you need very, very high energies, and that can have interesting consequences, okay? So you should really think about MHD simulations mostly in this context, and the more you go to the right, the more challenging it also gets numerically if you want to model those dynamics. Okay, so far so good. That's kind of the rough outline. And what I thought I'd show is just some simple examples kind of going into various regimes that we saw there, and just do simple toy problems, because ultimately we want to build up some intuition to understand, let's say, how do we launch a jet, or what do magnetic fields do to the accretion disk. But maybe we should start out more simply. Maybe we should just abstract the disk away. We might not really need that. We just take magnetic fields and we put that on the black hole. Right? If you assume that there's no plasma around, so you do this in electrovacuum, there's even an analytic solution for that, at least for non-spinning black holes. It's called the Wald solution, but hey, we want an outflow, so let's take a spinning black hole. The answer that you find looks roughly like that. That's actually a way fancier simulation than what we're talking about here. That's actually solving the Vlasov equation, so you're assuming that you have electrons and positrons that only interact through scatterings in the electromagnetic fields. But by and large, the thing will look in the following way. So you see the ergosphere here in green. You see that the field lines inside the ergosphere get dragged around by the magnetic field. There seems to be some kind of difference because all the field lines inside thread the black hole. Outside, you just bring in magnetic flux as sort of a boundary condition. And then this thing, if you were to plot sort of an outflow velocity, actually launches a jet. So you can think of that as kind of the prime example of what's called the Blandford-Snark process, where you can extract power from a rotating black hole by threading it with electric and magnetic fields in a regime that is called force-free, and that's basically just telling you that B squared over rho is very large. So we're kind of very much on the right of that. And there's an analytical prediction that tells you that the power of your outflow, your jet that you want to get from that, scales with the horizon rotation rate, that's just related to the spin, times the magnetic flux that you're putting on. That's a prediction, and there's many, many numerical studies in different regimes who validated that. So kind of that's the standard assumption whenever you talk about launching jets powered from the black hole itself. We'll actually see in a few slides that that's not the only way you can power jet-like outflows. There's many ways where you don't need a black hole. You can even do that by means of a rotating flow, and that might be interesting if you think in terms of hypermassive neutron stars, say from the problems maybe closer to here. Now, the interesting question, and that's a question that we have to ask ourselves throughout this talk, kind of which solution you'll get by putting a magnetic field on the black hole, because I'm going to show you a few different solutions that you can obtain, will depend very, very strongly on how fast you can supply magnetic flux on the black hole, right? Because as we'll see, black holes fundamentally don't like magnetic fields. They want to get rid of them as soon as they can. And so you can think in this picture that the flux should somewhat scale with something called a mass accretion rate. This is kind of the inflow rate of the field over here. In reality, this would be an accretion flow. There would be an actual plasma kind of from a disk supplying that here. This is sort of an artificial boundary condition that you put. But then when you do that, you can introduce then an efficiency parameter that basically asks, given the amount of magnetic flux that I have and given a supply of some m dot, I can define this parameter phi, and we'll see that that was very, very crucial in understanding the properties of the jet in the accretion regime. Okay, that's kind of, I don't know, black hole magnetosphere physics 101 for kind of preliminary for thinking about jet launching. And then if you want to think about how do you actually launch an outflow, how does that work? There's a very nice kind of cartoon that Sasha Tchaikovskoy always had, so I borrowed that here. The idea is the following. Think about, as we'll see, you don't, strictly speaking, need a black hole. It just can do that naturally, because if it's spinning, it has an ergosphere. But we could equally think, we just have a ball that rotates around, the field line sticks into that, and it's anchored somewhere outside. And so what the black hole is doing, or here this rotating sphere is doing, it's kind of twisting the field around, spinning it up. That thing already looks like a spring, at least visually. And we said that the magnetic fields, just like rubber bands, have an internal tension. So you wrap them up very, very strongly. It's like a massive spring. And then it pushes against the ceiling until ultimately it will break out and then launch the outflow. And that's a very, very simplistic picture of how that works, but that's a very universal one. So you find that if you think in terms of like angular momentum transport for like molecular clouds, or if you think in terms of angular momentum transport from protostars, or as I will show from hypermassive neutron stars as well, that you form in a merger, they will all kind of do this thing if they want to launch a magnetically driven or pressure-driven wind, what people would call that. Okay, so on the GR side, there must be something more formal that tells us actually how much power is in there, or how that works in principle. And so whenever you have something that sort of looks like it has a symmetry, of course there must be an effective killing vector mediating that, at least in a GR case. And so the question is, okay, if we want to figure out how much power there is, maybe there is some kind of conserved quantity that tells us what exactly to expect. And so in a globally symmetric space-time, for example, you can show that if you have a killing vector, you get a conserved quantity just in this way. You just dot that with your stress energy tensor, you apply Killing's equation, and you see that's conserved. That's a super useful relation because that's basically telling you that you can have conserved quantities like energy if you have like a time-lag killing vector, or angular momentum if you have a phi-lag killing vector, right? And so that actually gives you those conserved quantities in that notion. Now, how does it apply to the jet? Well, the important thing to note is there's two symmetries, or basically two things the symmetry can apply to. In case one, you basically apply it to the space-time itself, so you get a globally conserved quantity, like conserved total amount of energy or total amount of angular momentum. But the fluid can also have those symmetries. If you say the flow itself preserves that symmetry, then there's another quantity showing that this thing is conserved. Will probably take 5 slides, so we'll just pretend this relation holds, okay? Meaning that you can define a quantity that's conserved along in each individual streamline. So if you think in terms of your jet, there's something as you move out that's conserved, and that will dictate how fast you can accelerate. So if you want to know what's the Lorentz factor of your jet, you use that relation. We're going to see how that works. That's something you may have seen in kind of a mechanics type course. When you think in terms of Bernoulli's constant, this is where this comes from. It's a generalization of Bernoulli's law, where if you have this tube here and you have a flow going from the right to the left, you assume this thing is largely incompressible, so rho is constant and we don't really care about internal energy. Then as your flow goes from the right to the left, and you kind of go from this sort of big diameter to the small diameter, because you have to conserve your mass flux, the velocity here has to be higher than on the right. Because the flow has this conserved property, basically means that your dynamic pressure coming just from the kinetic part of your flow has to increase, and so your static pressure P has to decrease, and you can actually measure that. As you can see here in this difference sort of between the height of this water that you put in here, right? If it wouldn't be flowing, those would be equal. That's just telling you here's a higher sort of regular pressure, and here's a lower pressure because just you're moving faster, and so you have a higher dynamical pressure. Okay, what does that have to do at all with launching a jet? Well, a jet is sort of the inverse of that. Okay, and we can see this over here. So there is a jet from a simulation I did at some point. And for simplicity, we first talk about a hydrodynamical jet because this is kind of easier to understand how that will work. And so the idea is, okay, you want to know what's the terminal Lorentz factor, how fast are you going to accelerate out? And so if you want to accelerate, you need some sort of energy budget that ultimately drives that in the first place. So the idea is, if we assume we have some effectively gamma 4/3 law, then we know that the internal energy scales with the density. So we assume initially this gas is very dense and it's hot. Okay, so that's what we assume at the base. And then as the gas is expanding outwards, I'm going to convert internal energy into kinetic energy of this outflow, and this way I'm going to launch a jet. If you just plug this into Bernoulli's law, it's going to tell you that the Lorentz factor will increase as the density will decrease. You're basically using up internal energy to make your flow go really, really fast. Okay? What's the issue with that? If you want to have, like a GRB type jet with Lorentz factor of 100, well, if it would work this way, then your basically thermal part would have to be 100 times the rest mass energy, which is just crazy high. Meaning that for those, you need another contribution than what's accounted in here. Okay, and for that, now that we go to the MHD side, you can basically write down the same equation, again, things look very, very similar. You have this hydrodynamical part, HUT. This is like your standard Bernoulli's law. But then it gets corrected with a magnetic energy density, B squared over rho, and another term here on the right. And so what this is telling you is if you want to launch a magnetically powered outflow for a relativistic fluid, you only have those two terms that can do it. Okay, so only two possibilities. And so the first one, that's what we have already seen. That's a typical kind of collimator jet. So basically you're asking, if you launch in this Blandford-Nyack picture any outflow, the maximum speed that this outflow can obtain will basically be set by this parameter B squared over rho. So fundamentally, you're not in what we dubbed the crowbar regime. There's no jet. There's no way you can ever launch any outflow from that, right? So fundamentally, you need to be in this regime where the magnetic field is very, very strong and dynamically important. So we'll come from the left side over here. But then there's this other term. Maybe you could do it this way as well. And that's an interesting term. This is called Blandford-Payne type launched outflows from magnetocentrifugal winds. The analogy here is a bit more complicated, but you can think about it like this. So imagine you would have an accretion disk down here, and now the magnetic field is literally like a crowbar that you stick in. Then you can basically accelerate stuff outwards as it's coupled to the magnetic field. And you can do that as long as your magnetic field is stronger than your basically rest mass density, which is shown over here. So there's a certain thing that's called the Alfvén surface. At this point, the fluid will then decouple and then go out. It's basically like you kind of spin it up and it just flies away, right? And the maximum amplification kind of acceleration you can get is basically from this foot point over here down to where that happens. It's more complicated, but as we'll see, it's also important for say neutron star merger. So it's important for accretion disks in particular, should you be interested in like early planet formation, where that's one of the interesting contributing factors. So to give you some idea of how each of them work in a simulation, I will show you some examples. I will apologize. Some of the examples I will show will be with Einstein Toolkit. Others will use different codes. This one here was a toy problem that was simulated back in Frankfurt a while ago with the black hole accretion code. You can kind of see here a standard fishbone Moncrief torus. Here you can see the magnetization. You can also see the dynamical AMR that was used, but that's more for the show. I think the interesting thing to focus on is the color. So wherever it's red, this is where the magnetic field is dynamically important. That's setting your initial condition for later on for the outflow to accelerate. And then on the right, we're going to see the Lorentz factor. And then the movie is sort of co-moving with the initial front of that. So we're going to follow the flow as it's going out. So you can see this down here on the left. The black hole starts to accrete. You form a very, very strongly magnetized region around your black hole. You start launching this outflow. And then as you sort of zoom out, you can see, because here you have a huge potential reservoir of energy to accelerate the jet. Your material, as you move out in the sliding scale, starts to accelerate gradually up until it reaches a terminal Lorentz factor that's set by whatever the initial number was down right at the black hole base. Okay. So one thing that you might then be interested in, also on the technical side, if you want to simulate, launching jets from, I don't know, neutron star mergers or neutron star black hole mergers, you need to make sure that your code can actually handle this regime, which was a problem for many, many years. And maybe Zach can tell us the history because he was one of the first ones to simulate MHD for neutron star black holes. But anyway, by now, the technology has matured quite considerably. So for example, one thing I will say, like this new inversion scheme by Wolfgang Kastaun and others is really, really robust and has enabled much of the work that I'm going to show. So there's a lot of work that has been done to make this happen. This is one example, and this is exactly the other way of launching an outflow. This is how to launch a jet and a wind from neutron star merger remnants. There has been a lot of work on this over the past years. 2 or 3 years or so, trying to figure out if you actually have field that breaks out from the star and then collimates to ask, can hypermassive neutron star remnants form jets that are at least partially as energetic as jets powered by black holes via Blandford-Nyack? The challenge there was always to think, okay, by means of the analogy I just said, if the rest mass density at the surface of the star is too high, in particular down here, you may not be able to power any relativistic outflow just because the parameter that you start with that governs how fast you can accelerate, or the terminal value you can accelerate to, is just too low. So in other words, if this thing has a strong neutrino-driven wind, maybe there's no jet. This, by the way, is one of the few M1 simulations of launching an outflow with neutrinos and neutrino absorption included. The nice conclusion is it doesn't matter so much at the end of the day. It just basically changes the timescales, but the overall dynamics is very similar. The thing I want to highlight, though, and this is kind of a more like a tower-like outflow like we've seen in this example, where the star rotates, kind of makes the field lines go up like a corkscrew, and then just pushes stuff out. This thing has a second contribution, which we're also able to show, namely that this sort of crowbar term, this Blandford Payne type wind term that you see from accretion disks, is also present in the system. And so here on the right, we basically break up Bernoulli's law into the different contributions. This is your regular jet. This is b squared over rho. That's what you would expect. But here you have this additional term bt over k, where kappa is your mass loading factor. This thing is active exactly at the outskirts of the disk. The contribution is somewhat more mild, and you can understand that basically the geometry here of the flow isn't in your favor. So if you wanted to have maximum acceleration, the disk basically would have to be a bit more flat. The reason being, if you do that, your field lines kind of go out more and you have a larger lever arm, literally like if you take a crowbar and you want to open something up. That's how that works. Here, because everything is so steep, the lever arm is very, very short, and so you can't accelerate that much, but the contribution is there and it will still contribute 20 to 30%, which I think was a very nice demonstration of this. So overall, we've seen you can launch jets in two different ways. You don't need a black hole to do it. The accretion disk can do it. A star can do it. A black hole can naturally do it. So how can we ultimately apply that later on? And so with time, I show you actually how to apply that to the binary black hole problem. But before we can do there's a little bit more conceptually that we need to dig into just to interpret even the simulation results that we will be seeing. And so, for example, if you do one thing, if you zoom in to this image that we showed earlier, it's not just the accretion flow just going in. There's something weird happening down here where you have like this thin layer of like material going from the disk to the black hole, almost like attached by like a tiny thread. And that thin layer indicates something called magnetic reconnection. And what I'm going to do now, if you haven't heard about that, don't worry. You can think of this as being like a viscosity. If you've heard of like viscosity, let's say either neutrino driven or something that makes your accretion disk accrete on the black hole, that's something similar but for magnetic fields. That has huge implications if you want to make predictions for actual like high energy emission, like if you want to know where some of your gamma ray emission comes from those systems, that's what you would look at. But by and large, it's really like the same kind of concept. The main reason why we have to talk about this is because some of the microphysics assumptions, much like if you make assumptions on neutrino transport, where you say, oh, maybe I'm optically thick or I'm optically thin, also affect this process. And if you get them wrong, you screw up your timescales. And so that's something that I briefly want to introduce, because then we'll see that in many of the kind of toy concepts, much like the one we've already seen for the Wald magnetosphere that we looked at. And so the basic idea for this process is you're basically going to take a magnetic field that goes one way, a line, and another line, and if they touch, then what this process will do is just like a scissors, it will cut through the two field lines and then just stick them together in this way. So you're basically bringing in red field lines here, blue field lines here. This process, the resistivity, is just going to cut them through, stick them together, and then they move out in this way. And that's the fundamental dissipative process for magnetic fields. There's some theory that you can apply that largely comes from the 60s, from Sweet-Parker reconnection. But the main idea is there's something like a Reynolds number, it's called the Lundquist number over here, that basically tells you how efficient this process is. And what I will tell you now, and maybe not have time to tell you more at the end, this number, if you solve the MHD equations, say as they are implemented in Einstein Toolkit, are fundamentally wrong for many of the physical systems you want to model. The reason is there's basically physics modeling. It's like you need a different closure relation. So that one over here is not really good. Okay, so with that in mind, this basic process, we'll see some of the applications of that. Here I'm going to show you one thing we'll see in some of the simulations, namely that there's a counterintuitive behavior going on in how that works. And so you would think that as you make your resistivity smaller and smaller, there should be no dissipation. It's a fundamental theorem of MHD. If you don't have a viscosity, if you have a flow going around your black hole, it would never dissipate or fall in if you don't remove the angular momentum. Here's the same. If you don't have a resistivity, your field lines would just ever sit there and not do anything. But it turns out that as you kind of want to approach this limit, so you want to go to smaller and smaller values of this resistivity, you actually don't go to zero. So you would expect that, from basic theory, at some point you just go here. This is where zero is. The scale is a bit weird because Lundquist number is inverse, but kind of zero would be down here at infinity on the right. But what happens actually is that things level off. And so you end up with something called a plasmoid instability, forming these little magnetic islands. And their subsequent evolution can tell you a lot about potential transients. And we're going to see that in some simulations. Now, what I was saying when I said, okay, the physics is wrong, so we're basically solving the wrong equations, is that the real answer for this process shouldn't be down here. It should be 10 times larger, it should be up there. And that can have crucial implications. You can actually measure that. So if you do like more detailed physics calculations, in particular, if you do two fluid models that try to develop closures, or you solve directly the Vlasov equation, this is kinetic theory, just like you have to, for neutrinos, you have to solve radiation transport. And ideally, if you had a Boltzmann solver, everything would be solved. Here, it's kind of the same thing. If you introduce moments of the Vlasov equation, so with magnetic fields included, but no collision term, which makes those equations, technically speaking, not stiff, at least for most cases. You can go in and you can figure out what are the different contributions for those moments, and technically speaking, you can calibrate it. And one thing that we did recently, this was led by Abby Moran at Columbia, I was working with Lorenzo Zironi there. We actually extracted kind of what is a good closure that you can actually put in a numerical simulation, such as any kind of resistive MHD code that you would run in a dynamical spacetime, say, or in also a static spacetime for black hole physics. And we worked out a very simple term coming from that. So Abby ran basically a large number of simulations, analyzed them using some effectively simplified machine learning methods. And then you figure out that the true relation is actually very simple. And there's good physical reason for why this is. And if you have questions, I can tell you more later. But the nice thing is, just like as for a neutrino closure, you can put different limits in. We can do the same thing with magnetic fields as well. And that can have direct implication. OK, any questions so far? Because what we're going to do now, we're going to apply our newly gained knowledge to some of those simple test problems of like magnetic fields interacting with black holes. And then we can, at the end, talk about how all of that plays together if we want to understand in a realistic accretion flow, say, around the binary. Yep.
I'm interested in the initial data. So just for a single black hole, how would you construct your matter, initial distribution of matter, so that you get these kinds of jets?
So that you get these kind of jets. We're going to talk about that after that. The question, oh yeah, thank you. So the question was, what do I have to put as initial condition so that I get a jet, right? And so what we're going to do here, so all of this are initial conditions, right? They're simplified initial conditions. So initially we said we just put the magnetic field on. Now we put the magnetic field on in a wind. After that, we're going to put the magnetic field on from large scale accretion, and then we talk about disks. So we basically covered that, but we're building our way up. Because I think the problem is if we just directly jump to the disk case and we say we just put this disk and hit enter, we miss out some of the things, some of the intuition that we actually expect to see. But yes, so that's what the rest of the talk will be. And then ultimately, we're also going to see some results for thin disk type model that we use there. Yeah. OK, so simplified initial condition now, rather than putting something directly on the black hole, we can do a wind tunnel experiment. We could say there's a wind blowing magnetic field and plasma on the black hole. What actually develops? And so this is an actual MHD simulation. It's also a very well-studied problem. It's called Bondi-Hoyle-Littleton accretion. And we're discussing this because it's important for some of the things we're going to see, that the system will have intrinsic scales. Right? So basically what we're doing here, maybe in your language, rather than running an initial equilibrium solution, right, like a separate code or problem that would do this, we're going to grow a disk around the black hole organically by just throwing stuff on. It's way more expensive to do, but you can do it. And then you can actually see what kind of natural disk forms. And that's important if we later on want to talk about what's the realistic accretion environment of a supermassive black hole binary. It's not going to look like any of the initial solutions that you will put. And we're going to talk about that as well. How we can organically construct that. Okay, so what are the basic parameters in this setup? You basically have a wind coming in your wind tunnel, and so the wind has a certain speed, much like for the car, you'd have a certain speed of stuff coming in. That's here on the right. This is this V infinity. And then there will be a gravitational sphere of influence, right? Because if you're very far away from the black hole, your wind is just going to blow past. But there will be a point at which the wind will sort of be bent, just like you can see here, and kind of start wanting to go towards the black hole. And that's called the Bondi radius, which here goes with V infinity squared. So that's kind of the number that you can build that governs that. And then once you go there, there's a certain time it will take for matter to fall into the black hole, which goes like 1 over V cubed. And if you think in terms of relativistic problem, V is less than 1. So this time scale can be very, very long. Okay, compared to sort of the dynamical time scale that you have near the horizon. It's actually a very challenging problem. So what I will show you now is a set of simulations that recently one of the students at Caltech did. He's actually graduating tomorrow, so I'm going to fly back tonight for commencement. But what he did for this work is he used the Summit supercomputer for 800 GPUs, and then we integrate the system for 40 times the dynamical time, which is a very, very long runtime for this problem. Think of like second-long accretion flows that you would have in the past of a neutron star merger. Okay, so we're going to see the wind coming from the right. The black hole is right at the center. You're going to put this in, and you can see that over time, there will be an outflow from the black hole. There are large-scale jets that are developing, but somehow it's not stable, right? The thing is wiggling around. Maybe that depends somehow on the wind speed. Definitely the jets are bent, as you can see initially. There's some kind of weird outflows that happen over here on the left. And we'll see that most of this dynamics is very generic for a black hole embedded in a very strongly magnetized flow. And we'll understand a little bit on how this works in detail. But you can really see there's sort of all this variability. It changes over time. The jet switches off. And it's very characteristic for those flows. It's not just like you always have a jet on, which, as we'll see, is also important for other kind of applications. Okay, you can watch it once more. Black hole gets all of the magnetic field in. You launch an outflow. It wobbles around, switches off, switches on. And we can understand this a bit. So now, in order to the question of like, what initial conditions should you put? Well, let's basically look into something for these thick disks in terms of accretion states 101. Depending on what you put in your initial condition, you put that in a simulation, you're likely going to end up with two results. That's not exactly true, especially with radiation. You would get another state. If you had sort of a large-scale accretion, as we'll see, you get another one. But by and large, if kind of somebody would ask you, like, what does a flow around a black hole look like, there's only like two main categories that people like talk about these days. One of them is called standard and normal evolution. That's also, if you think in terms of like a disruptive neutron star black hole merger or a neutron star merger that collapses to a black hole, that would most of the time be in this regime. So you have kind of this thick, puffy disk. Some stuff that goes in the black hole, we already learned the basics of like how you can launch an outflow from that. It will strongly depend on how much magnetic field you have. You can see there's some stuff coming with the jet. The jet is sort of slightly bent. If you compute an effective jet efficiency parameter, because we already talked about it depends on how much magnetic field can you bring on, or here the question is basically what's actually providing the energy for the jet? Is it really the black hole spin, or is it just the energy of the matter that you accrete? In this regime, it will always be the energy of what you're accreting. So the jet luminosity compared to like the accretion power, m dot over c squared, will always be less than 1. Okay, so in the analogy of this crowbar regime, we're kind of right in where the ropes are. We're not in the crowbar regime, but we're also not in the rubber band regime. So the magnetic flux on the horizon characteristically is less than 50. If I only tell you one number from this to take away that something changes when you reach 50, or technically speaking, when you reach 25, because if that number is less than 25, you'll not get a jet. Okay, so there's some kind of characteristic number that you can compute that tells you when you get that. And then the other important thing, which we won't talk a lot about, what actually makes stuff fall on the black hole is determined by something called a magnetorotational instability. So there's instability in the disk that creates turbulence, and then the turbulent torque on the material makes you ultimately, turbulent stresses on the material makes you ultimately fall in. Now, within some of the examples we've seen, the accretion flow can work very, very differently, and those accretion flows are called magnetically arrested disks, or for obvious reasons, they're called sane and mad. The reason for that is the magnetic flux, if you look in the funnel region here, is much, much larger. You have this huge amount of magnetic field that's being put on the black hole. It's going to power this outflow. And in this regime, if you measure the jet efficiency, this is larger than 1, meaning here you're actually tapping into black hole spin. So our analogy for this Walt magnetosphere initially is the one on the right, not the one on the left. Okay, so now you already know that most of the time when you want to launch an outflow, let's say from a neutron star merger, you'll not be in the right regime, which is not exactly true because the regime at some point can change. There's very nice work by Gottlieb on that for like neutron star black hole disruption disks. But by and large, you'll mostly be in the left side. Now, the right side is interesting because that thing can feature very, very strong feedbacks. It can feature outflows. And most importantly, angular momentum in the disk is not governed by the magnetorotational stability to a large extent. It's governed by something called magnetic flux eruptions, which is something very counterintuitive. But we're going to get there as well. And then in this regime also, the jet is actually able to spin down the black hole because you can extract so much rotational energy. If you look at some of the recent simulations of collapsar works, this is like collapsing stars into a black hole, launching a jet out, breaking out, producing a long gamma ray burst. In those systems, the black hole spin can go to below 0.2 or so because of that phenomenology rather rapidly. And there were even like some works by Masaru Shibata's group recently doing like a 2D numerical relativity simulation, actually tracking the spin down from that. So that's actually very interesting, I think, for those cases as well. Now, the question is, for what system is which thing important? And there's some observational data. So if you think in terms of the Event Horizon Telescope, then very close by near the event horizon, you can actually make a measure, not just of the color there of the emission itself, but you can look at Faraday rotation. It's basically telling you that in the presence of a magnetic field, you're going to put up a net rotation of your polarization vector. And that thing you can measure, And you can infer that that's most consistent with a strongly ordered magnetic field near the horizon, meaning that, if you want to model some of those sources, you'd likely be in that regime. So if you're interested in, what does a supermassive black hole binary does, maybe it will be more on the right, but that's debatable. Well, we can talk a bit more about that. Right? And so understanding that those two regimes behave differently is very, very important, because if you want to set up your initial data, you need to pick in which side you are on. That's like an initial condition. You're putting in, if you have very weak magnetic fields, you're going to end up on the left. If you put strong magnetic fields, loosely speaking, you're going to end up on the right. Okay, so what makes this configuration so bizarre? We saw in the movie of this black hole in the wind tunnel, there was stuff coming out of the black hole, like that was being ejected, and that's a characteristic feature of this regime. Basically, if the magnetic field eats too much, if the black hole eats too much magnetic field, at some point you're going to get rid of that. The reason being that as you oversaturate, the field lines here are going to touch right at the equator, and then this magnetic reconnection process kicks in. It's going to basically cut off half of this funnel, or maybe like a third of this funnel, and then this flux is ejected back into the disk. And ultimately, this is what's disturbing the disk so much and propagating out. That's what's dominating the angular momentum transport, right? And so all of kind of these physics that we talked about here come together to tell you, A, how you get a jet, then that the steady state at some point has to self-limit, self-regulate because of magnetic dissipation. And then there's a feedback from the black hole on the accretion flow, which is something that can really have dramatic consequences, as we'll see. And so if we take a still image of this simulation, we find exactly that morphology. You can see here that as the black hole oversaturates, there's the stuff that's being ejected that is moderately magnetized, low density, and that's exactly your ejected flux tubes, as you could see there. So that black hole, for sure, for part of its life, is magnetically arrested, right? And it's spinning the black hole down via Blandford's Nyack. Let me see, what is the time? There's some interesting physics going on in there that's largely related to how do you actually launch the jet in the first place, especially if you don't have a vertical magnetic field. So most of the time, let's say, think of a neutron star black hole merger. You're disrupting the neutron star. You're going to form largely toroidal fields. So your magnetic field will go around the black hole spin axis like that. It will not go up. And so you need to do something to the field in order to launch the outflow in the first place. And that's actually what we investigated here, because the wind had no magnetic field that could ever power a jet unless you do something to it. So there's kind of a dynamo amplification process going on. I think in the interest of time, we'll skip that. But if you have questions, we can talk about it later. This has very strong implications if you want to explain also delay times between seeing a GRB, let's say, and the merger of a neutron star. Kind of same physics going on there as well. Okay, we'll skip that part too. But I wanted to show that because the wind speed, as we saw in this initial connection or comparison with the Geminga pulsar, you can see if you have very strong wind speed, the wind is so strong it can actually bend the jets, whereas if it's very weak, they will just go out. So you can really nicely see this morphology, even that you see in an observation in your simulation as well. Problem is, simulating like small speeds, and we've seen the time scale goes like 1/v cubed is very expensive. So one had to like fudge this a bit up here to make sure that it's not that much in terms of like moving the inner boundary. Okay, so now what I want to do, just so I get a better feeling for what the initial conditions would look like, I want to talk about how can we do this more realistically? Where would the black hole in most cases, and this is largely for supermassive black holes and supermassive black hole binaries, where would they get their matter or their flux from in the first place? It needs to come from somewhere, and largely it comes from large-scale accretion. And so you can ask the very basic question, okay, if I just go up, think about like going up like the highest building on campus and dropping something down and then seeing how it hits the ground, you can try to do the same thing. You try to throw in something from ideally galactic scales, which is very hard because that's 6 orders of magnitude difference to your black hole size. And then you ask, how does that material ultimately makes it on the black hole? Do you get a jet? Do you get feedback? Do you get any of this? And later on, we'll see that for the black hole itself. The physics works very similar to this wind example, just that now, because there's no net speed, this characteristic scale, the sphere of influence, is now set by the sound speed, set by how hot the material is, not by how fast it moves in a preferred direction. And then physics is still the same. You basically get a steady state accretion rate, goes like 1/CS cubed. And here, one of my postdocs, Aris Lalakos, has recently done some of the largest contiguous GRMHD Bondi accretion simulations to date. Okay, that's a lot to take in. But basically what that is this is a hammer simulation where the outer boundary from which you want to accrete is 4 orders of magnitude bigger than your black hole, which is very, very challenging. And then you run this thing for the equivalent of 13 seconds in a neutron star merger, and you ask, what does the steady state look like, the feedback on the black hole, and the resulting flow. And the nice thing that he found there is actually quite nice. I mean, the flux eruptions are still there. They propagate all the way out, which is cool. So the same kind of phenomenon. This angular momentum transport is really, really interesting because the flux tube really stay coherent and they move all the way out. On the technical side, by the way, this is enabled by a logarithmic grid, so the resolution is not so high. It's less than 1,000 cubed cells, so it's not crazy, unlike what you normally see for GPU simulations. But it really kind of shows you that now with the technology that's there, you can actually do that. What's interesting for this black hole is during his PhD, Elias had actually discovered a new black hole accretion state together with Sasha Tchaikovskoy down here. It's called the rocking accretion disk state. Don't have a lot of time to talk about that, but basically what happens is as the jet weakens, it can kind of randomly sort of go around, transport angular momentum on your flow and cause a net feedback, then switch off, and then here in this example become magnetically arrested again. So what this means on a practical level, if you think in terms of like what do you need on the computational side to study this problem, what I want to point out with this many lines here is basically just one thing. So when you look here, here is the limit where we go magnetically arrested. This is when we get this jet that goes all the way up back to effective galactic scales. But then it switches off for a short time period, short in quotation marks, and then later on it can just switch on again. And this is really, if you think more in terms of neutron star merger timescales, if you're more familiar with that, you basically are on for a few seconds, off for a few seconds, and on for a few seconds again. So if you want to study any such problem, you need enormous amounts of computational time, or here in like black hole units, it's like 10 to the 6 m in a simulation, which is very, very long. You really need the ability, and I think this is where GPU-based computing can get us these days, because it only scales linear with time. It doesn't scale like the fourth power if you change the resolution. In order to do this, right? So if you want to do anything, those kind of problems, I think you need GPUs. Right? So just to make the point more, you should all look at AstroX and the new Grail version and all of those things. Okay, on the physics level, but you know, I just mentioned that actually the simulation showed that the accretion rate, kind of relative to where you feed, is sort of very universal. This is a surprising result because it doesn't depend on how much angular momentum you have. You could have thought if you kind of go faster around, you accrete just less, but that's not the case. It doesn't seem to care so much. And Elias really managed, and this is still surprising to me, to get a precision out of that that's sort of accurate to the second digit. So before that, I think the community had accuracies of like around 0.5, and he managed to show it's more like 0.66, which really means there's a net modification in the flow that's going on. And that's really, really interesting. And what it also means, if you actually plug into this relation, sort of the scale separation between, for M87, where we saw the EHT image between sort of the Bondi scale and the black hole size, actually the matter that makes it to the black hole is only 1%. So it's really, really strongly suppressed, meaning that all the stuff intermittently has to go out, has to be ejected again. And that's important because that means that you get a net feedback on the stuff that's actually coming in. So it's not like everything just goes in, like in the spherically symmetric example. It's more like in one way it goes out and the other way it goes in. And we're going to see that at the end with some stuff we did for the binary. Okay. Any questions on that? So far, we just threw stuff on the black hole, either like vertical flux, either a wind. Then we just went up to a high tower, threw something in. Now what we can do is let me see how we are with time. I think we have two options given the time. We can either talk about the example of what happens if we throw a magnetic dipole in this black hole. This can tell you something about what happens if you have, let's say, a neutron star collapsing into a black hole and what transients you see there. This is actually a very nice Einstein toolkit simulation we did recently. Or I can directly jump and tell you something more about large scale accretion. Okay, show of hands. Who wants to see neutron star black hole binaries? Who wants to see black hole binaries? Okay, nobody. All right, we will talk about that example. Or better say, actually, let me do the following. We can split the simple example. I think we don't need that really. And we just talk about sort of the neutron star black hole directly. And then if we have time, we talk very briefly about the black hole binary also. So for the neutron star black hole binary, it's actually interesting because you can ask the first question, let's throw a neutron star into a black hole. But first of all, let's do it organically. Let the thing just collapse in on itself, meaning it becomes gravitationally unstable. Now, the important question there is what actually happens with the magnetic field that's in the exterior of the neutron star, because as we've seen in all examples before, if you put magnetic field on the black hole, it doesn't really go in, at least not if it's in this very strongly magnetized regime. So there will be some dynamics, and those dynamics could be observationally interesting. Okay, so maybe there's something coming out again at the end of this. The interesting thing for that is, in order to understand how that works, we have to look into MHD waves, because something will happen with the magnetosphere, and if we are in the MHD regime, that's good because there's exactly two types of waves. One looked like that example that you can see there. It's like a transversal wave. It's called an Alphan wave. That happens if you take the magnetic field line and you shake it very, very hard. There's like a wave that will propagate all the way out. And the velocity of that will basically depend on also the magnetization of the background, right? So if you're in a very strongly magnetized regime, the Alphan speed goes to the speed of light. If you're in a very weakly magnetized regime, that can be very lower than the speed of light. But everything that we're considering here is basically that those perturbations on the magnetic field itself move at the speed of light. So the example that I'm showing here is you take a crowbar and you do something to it that's so violent that suddenly a wave is propagating along it at the speed of light. Okay, this is what we're looking at. And then there's a second type of wave, and that will be the wave that's largely excited in this collapse type case. That's like a sound wave, just as I'm talking. It's a wave that's not bound to the magnetic field, but it's magnetically supported. And then within this MHD regime, interesting things can develop. And so the way you should think about that is the magnetic field is weird in a way that it's kind of weaker further out and stronger closer in. And that means if you launch a wave across sort of this background, it's like a potential well, right? So you would go down the potential well, you're going to gain energy. And that's exactly what that sound wave is doing. There's a mathematical expression there, how the wave energy goes. But basically, by and large, it just goes out, and then the wave wants to accelerate over time. Okay, and if you plug that into the net speed that the wave will have, at some point, the wave wants to become superluminal. And so something has to happen because there is no superluminal propagation in the system, right? So you basically talk, you get faster, 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 and then something has to happen with this wave as it wants to hit the speed of light. There's a nice mathematical solution to that was obtained 2 years ago by Andrei Belaborodov. It basically shows that in these environments that we have here, these waves will go as close to the speed of light as allowed by this magnetization parameter. In the realistic neutron star background, the magnetization parameter is 10 to the 9, and so modulo like some modification from the wavelength, you reach crazy high Lorentz factors, like 10 to the 8, 10 to the 9, the fastest Lorentz factors that you get in the universe potentially. And so the way then the system regulates itself, because you really want to violate relativity almost, is it forms a very strong shock, which is called the monster shock, just because the Lorentz factor is so extreme. And so that means is as this neutron star meets its demise, there's something very crazy going on in the magnetosphere. You accelerate locally to Lorentz factor 10 to the 9, and that can have observational implications. And what was realized by now is this can be a nice probe for fast radio bursts. Let me just go here. Maybe at the bottom, there's a very nice kinetic simulation by Arno van Tikam and Armie Levinson, basically showing that if you do this under more realistic conditions for collisionless shocks, you actually drive a synchrotron maser just ahead of this thing, and that could help explain the galactic FRB-like emission. There's like one galactic magnetar that's been shown to do FRBs about 5 years ago, and that thing could potentially explain that. So there's very interesting physics that's going on, but from our point of view, if you ask about, what can your numerics do? Well, technically speaking, they can do that. They can actually capture the formation of the shock, reproduce this analytic solution. But I will say, this is a simulation with Einstein toolkit, by the way, with some modified version of Illinois GRMHD. But what I will say is, this thing, to get that to work, took about 9 months, just because the stability of the code to maintain that solution is so critical, and it took a while to really get it stable enough. And I can tell you, like in all detail, what you have to do with it to make that work. Because otherwise, what would happen is the shock would just disintegrate and it would be gone. But we now have I think, numerical knowledge as well to actually capture those kind of phenomena. Now you can see, as the neutron star goes in, you pull very strongly on the magnetic field, and then you're going to launch this extreme shock. But of course, there are limits, and so at least with what we can do with Einstein toolkit right now, we cannot go above a Lorentz factor of 30 or so. That's at much what we can do. I think in principle, one could push and try to do this with higher resolution. If you had adaptive mesh refinement and crazy high resolution, I think we could probably go to 100. But that's TBD. Okay, but by and large, we can reproduce this, and we can make a nice prediction for what happens in this case. There's something nice also that goes on that we were able to do. This is also really cool. After all of your neutron star is gone and you just have sort of this magnetic field on the black hole, I can actually show you a simulation outcome here, what happens. So black holes don't like closed magnetic field lines. There's a fundamental theorem by Thorne and McDonald that says the field lines, cannot be closed. The black hole can't support that. And so you can see here that the field lines get all of dragged out. You end up with the split monopole configuration, which almost look like what you have in the jet. But then we can even track all of the quasi-normal modes from the black hole as it's ringing down and as it gets imprinted into your actual flow. And that's still an ideal MHD simulation. It's literally like vanilla equations that you solve, but the code is so stable that in the strongly magnetized regime, we can capture all of that and you can compare it to the black hole quasi-normal modes and it's roughly consistent with what you expect there. So I think it's really, really cool like how much these codes have matured at this point. Okay. All right, let me skip that. And you could also, because people voted for a neutron star black hole, you can also do the more realistic case that the neutron star gets swallowed by the black hole. And here we focus on those cases where the black hole is much more massive than the neutron star, because those are the ones that LIGO keeps observing. And so in those cases, there's no remnant matter that is around. There's no counterpart you could power from that, so no gamma ray burst. There's no kilonova afterglow. But the magnetic field is still here, and so you can ask, can we make a prediction for other types of transients that you might be able to see? And the nice thing is, at least from the simple example, we said, okay, there should at least be a monster shock, so maybe you should get an FRB. And that's indeed what happens. So we did kind of the same simulation. And the nice thing is, after spending 9 months to make the code stable, that thing worked on the first attempt, which was great. So it usually never happens, but that worked. And so we basically solved the MHD equations everywhere outside. And then we have kind of a switch that tells us when we're inside the neutron star and when we're outside to make that transition and make sure that outside the floors are set to the right values. And we find exactly the same behavior. We see that there's a monster shock formation, the field gets ejected, but crucially, something else happened. And I think this is really cool. So this is a video that Yunsu made after the merger. This is for a field where the field is now misinclined to the orbital axis. Okay, so you have an inclined dipole, and now the dipole retains angular momentum. And this is actually what the simulation showed, which is really, really cool. If you haven't seen a picture like that, if you simulate what a pulsar magnetosphere looks like, so a rotating neutron star with a dipole, at some point, the dipole would rotate faster than the speed of light, so the field lines open up. It's exactly what that looks like. Okay, so here's kind of such a simulation for the dipole. You have these open field lines that go around. It's called the pulsar wind. I basically managed to demonstrate here for the first time that this system forms what was predicted to be a black hole pulsar state. It's very short-lived because, again, the field doesn't like the black hole doesn't like the magnetic field, but we're able to demonstrate that, which is really cool. And that's Einstein took it, so very cool too. So this is what this looks like, kind of a still image, which is really nice. So you get this kind of spiral type shape that's going out here of opposite polarity, and then it's kind of all dragged around by the rotation of the black hole. And the total lifetime of this is less than a second, so it's a really, really fast transient. But there will be a transient associated with that because you will have, again, magnetic reconnection in the striped wind. I won't talk too much about that because I think that brings us probably a bit too far. But if you were to simulate that for a pulsar, like here, what Benoit Cerruti has done, you can kind of see that those stripes extend all the way out. And as they go out, you have this ultra long current sheet that sort of whirs around. So everywhere where you see color, this is where magnetic dissipation happens. And you're kind of eating up a large fraction, like 30, 40%, of the magnetic energy in this wind, and that will all be dissipated ultimately into X-rays, which is very, very nice. So you can also predict that a neutron star black hole merger, even if there's no remnant matter left behind, should have an X-ray afterglow just from dissipation in the black hole pulsar magnetosphere. Okay. All right. Any questions on that? Okay, we can also take questions later. I will use the last 8 to 10 minutes or so, and just for those who voted for binary black holes, I'll very briefly tell you what you can do these days. We probably don't get to go through all of the details. We've done several work at stages of the evolution recently, but I'll tell you a little bit about interesting things that we have done, given the concepts that we have written. Oh, I lost my microphone. Okay, guess that's telling me the talk should end. All right, so I won't say too much on the science side. I mean, it's very, very interesting in the case of like recently detected stochastic gravitational wave backgrounds to ask the question of like, how do supermassive black hole binaries at parsec scale separation evolve? And as we look to the hopeful future, I guess, then we also can ask the question of if we actually detect with space-based gravitational wave detectors the merger of supermassive black hole binaries in those environments, what kind of multi-messenger counterparts would we get from those? And so the question then is, how do we connect ultimately the simulations that you would do that resemble more like the ones in numeric relativity or kind of accretion onto a binary itself with the actual sort of cosmological scale initial conditions here, some simulations done in the group of my colleague Phil Hopkins, where you can on large scales form realistic accretion disks, which by the way, and I don't get to talk about this, don't look like anything that I've mentioned in this talk. Like there's a new kind of disk solution, which may or may not be real. This is a hotly contested topic, but those may evolve very, very differently. And so the question is, how can you do the intermediate way? And before we talk about, accretion on the black hole itself, we can again, from our toy experiment, ask, how would you actually organically build the disk? So what is the right initial conditions? Let's say either if you have a black hole binary close to merger, or if you have a parsec scale separated black hole binary. And so what we did with the student, we actually looked, and also Aris, we actually looked into how you can do this computationally. How can you actually like naturally assemble a disk around a parsec scale separated binary? There's one thing that really made this a bit hard. And that's the fact that the physics on galactic scales is very different than what your normal intuition would tell you. The reason is there's a cooling instability in the interstellar medium that actually doesn't mean that stuff just go in spherically symmetrically. This is for M87. M87 is an elliptical galaxy. If you look at images on large scale, it really looks like this, like a blob with like some overdensity at the center. But as you zoom in, there's a cooling instability going on, which basically means that what reaches, so the black holes, is not spherically symmetric. It breaks up into those filaments, which, because they're strongly cooled, will be cold. And so you get cold accretion streams that go in. And so a simple toy problem, let's say what Aris has done, just throw some matter in, doesn't really hold for those scales. And so what we did is following a very nice example set by Sean Ressler, a multi-scale simulation. If you look into the current black hole accretion community, there's kind of a very, very big push to how can you actually extend the simulation I was showing not to 10 to the 6, but to 10 to the 9. So how can you just make it like 3 orders of magnitude bigger? And so the idea is you basically do multiple simulations in one, where you sort of freeze the outer scales, then you do the inner scales, then you do the outer scales again, and you have some sort of zone cycling. Here we did that in a very simplistic way using technology that Minghao Guo, who is a grad student at Princeton, has developed, where we sort of do basically first an outer scale simulation, then we just refine more, and then we run it again and refine more, and then see how that connects to the binary. And so the picture we should have in our kind of cartoonish assumption should really be that. And if you ask how much did the simulation cost, there's a number, and we're very thankful to Summit Plus and OLCF for allowing us to do that, because that was really, really a challenging simulation. And when you do that, you also have to make sure that you resolve enough binary orbits. So we actually had to simulate that for 130 binary orbits, together with all of the outer scale. This is what you get. So if you ask, what is one way that you could form such a circumbinaries, what it would look like? This is what it is. You basically get a collision of those cold streams. They circularize at a scale of about 30 parsec. The binary is here at the center. You can kind of see the 2 black holes marked there. The interesting thing is, because the orientation of those cold streams is random, you can end up with a disk that's sort of not in plane around the binaries, more that's like, in this case, almost 90 degrees. So it's a really, really weird configuration that you form. And actually, over galactic times, this will change because all the cold streams that are coming in are random. So your disk is kind of, ultimately on large scale, it's going to do that. And so what we then did is we evolved the system, again, from what we learned about, what happens when you launch outflows from this. This is a Newtonian MHD simulation, by the way, because we cannot by any means go down to the event horizon scale. But still, jet launching in this way works the same. It's kind of a magnetic tower type effect. So we launched jet-like outflows from both of the kind of pseudo black hole accretion sinks at that point. And then if you look at what this disk is doing, this is what I tried to allude to in these cosmological simulations, you end up with an accretion disk that's completely unlike anything that we've discussed so far, because the accretion disk has so strong toroidal field that basically the entire disk is in a crowbar-like regime, right? Where the effective plasma parameter is like 10 to the 3 inside the entire disk. There's interesting questions of whether this is stable or not if you include radiation, but that's currently what we find. And so our initial kind of investigation to this question is, okay, maybe supermassive black hole binaries evolve under very, very different conditions than what we normally consider, or let's say what a neutron star binary would do. And I can tell you more about that if you're interested. And so motivated by that, we actually did some also more investigations of this regime just to get some idea for what is actually going on. And so maybe the thing I will end with very briefly is I'm going to tell you how now the stuff that we discussed for single black holes, at least partially, translates also over to the binary. So this is something where you should think we're now going closer to merger. This is not on parsec scales, but we're now substantially below that, maybe like, I don't know if I had to guess, maybe like 10 to the minus 2 parsecs or so, or 10 to the minus 3 parsecs. So on those scales, what will happen is you're actually going to feed the black holes themselves, and then interesting things can happen. And Zach is telling me I should not tell you about this. All right, so I won't. So, but what I will tell you, and this is maybe I just end there, is that we can now take our intuition from single black hole and also apply that to the black hole binary. Namely, if you think that most black holes are in the same regime, that's actually what has been studied over the past decade or so using 2D viscous hydrodynamic simulations. So if you think all of our knowledge, if you want to interpret, let's say, environmental effects in LISA or otherwise want to look at the evolution, comes from 2D simulations with an alpha viscosity. And there's a few very nice works, especially done at JHU in Rochester, trying to also do this for GR-MHD close to the merger. But by and large, they look like the same regime. And so by everything that I told you is, wait a second, shouldn't there also be a mad regime? And since I'm not allowed to tell you how that looks like, I will tell you we actually found it using another very, very expensive simulation. And we now understand that if you have strong magnetic fields in the system, you can actually get a flow around the black holes that look very, very similar to what EHT sees, and that can change orbital angular momentum transport. Actually makes the binary spiral in and not spiral out. And it can also tell you something about multi-messenger counterparts, but you'll have to ask me over lunch. Thank you.
Yeah, indeed, we should continue conversations over lunch. Thank you for the very interesting talk, as always, Elias.
All right.
Thank you.
Thanks.
So, is Johnny there?
Hello. Yes, I'm here. Can you hear me?
You're just fine. Let's get you set up on Mr. Zoom here. There we go.
All right.
Just a second.
Great.
Just a second. Stop.